Okay, so how was, I assume everybody's read chapter 21, or chapter 1. How was it? Easy? Alright, because I'm going to do a kind of a review, and then we're going to move into chapter 2. Let's start out with what I want to do. I'm going to do this a couple of ways, and I want to cover this basic sink filter, which is actually a little bit in chapter 4. So when we talk about decimation in a lecture or so, we know what a digital low-pass filter is. So if I have a sequence of inputs, let's just call them x sub 1 at some time, and I'm assuming you know these are sequential samples that are coming into a filter, so they might be 10 nanoseconds apart or 33 nanoseconds or a microsecond or whatever, but I've got a bunch of them. And I make a filter which averages 4 of them. So it averages these 4. Then the next output it averages these 4. And the next output it averages these 4, and so on down the line, right? So which sample occurs earliest here? This one, right? So this might be at t equals 0, t equal 1, ts, t equal 2, tn. I'm boring you. So I want to take this, so my output would be the sum of these 4, which would be, let's just say y of 3, because I have to wait for all the samples to go through. The next output would be y of 4, because I have to sum all 4 outputs. The next sample, or the next output would be y of 5, etc. Does everybody follow? So if I write the z transfer, or z transform of this equation, I can write it as y of z, which is my output, is equal to x of z plus x of z to the z to the minus 1 plus x of z to the minus 2 plus x of z to the minus 3. And you say, gee, you're not challenging me, but I have to ask the trivial question anyway. This sample here would correspond to which one in my first output? X of 0. This one would correspond to x of 1. And the z to the minus 1 corresponds to 1 delay. Z to the minus 2, 2 delays. Z to the minus 3. Okay. So I can write that h of z No, the number doesn't matter. You could call it whatever you want. I just picked these because you have to wait 3 clock cycles, or 4 actually, for the output to come out. So I just did it so it corresponds. But you can call these samples whatever you want as long as they're sequential. And that's 1 plus z to the minus 1 plus z to the minus 2 plus z to the minus 3. And does anybody remember what I did last time? I took that, so this could correspond to these first output, the second output, the third output. I'm going to multiply the, now you need to know this, alright? I'm going to multiply the top and bottom by 1 minus z to the minus 1 over 1 minus z to the minus 1, or multiply it by 1, right? If I do that in the denominator, I get 1 minus z to the minus 1. And then in the numerator, I get, I'll do the first few. I get 1 minus z to the minus 1 times 1. Then I get plus z to the minus 1 minus z to the minus 2. Then 1 minus z to the minus 1 times z to the minus 2 is z to the minus 2 minus z to the minus 3, etc. until I end up finally with what for 4? 1 minus, so these two cancel, the 3's cancel, 1 minus z to the minus 4 over 1 minus z to the minus 1. And this is a moving average filter, and this is just like in the stock market. I got my 4 samples here, my 4 days, then my next 4 days, and my next 4 days. This is a z transform of the moving average filter used in the stock market. Any questions? And so if I averaged 8 samples, how would this change? Yeah, it'd be z to the minus 8. Okay, so I want to go through and I want to use all the stuff we talked about last time and plot this filter response, because we'll use it, like I said, later. Okay, so I'm going to write my filter. Let's do it for k equals 8 samples, or averaging of 8. So then I get h of z is equal to 1 minus z to the minus 8 over 1 minus z to the minus 1. And if I plot that, if I ask what are the pole, let's multiply the top and bottom by z to the 8. So I get z to the 8 minus, well, first off, one of the things I said last time is that I have to have more or equal number of poles of zeros. Do I in this circuit? How many poles do I have? Well, you know what? Let's multiply the top and bottom. Right, 8 poles. Let's multiply the top and bottom by z to the 8th over z to the 8th minus z to the 7th. Now I'm going to rewrite it even a slightly different way. It's right. Hold on. Z to the 8th minus 1 over what? Z to the 7th times z minus 1. So how many poles do I have? 8. So let's plot the poles. That's easy, right? So there's my unit circle. And the poles I have right here, I have 7. And then I also have a pole where? At 1. And I know I need that pole there because remember when I did my distance away from everything, that cancels the 0 at 0 and that gives me my low pass response. Does everybody agree with that? Now where are my zeros located? Yeah, they're distributed around. So I have a 0 right here at DC, 1 at F sub S over 4, and I've got them right in the middle here. So for example, what's the location of this pole? Square root of 2. Now, there's no deep thought. I know that this unit circle is 1, right? So it can't be root 2, because that would be beyond 1, and I know I'm within 1, right? And then what's the other location? So how would I write that in my numerator if I wanted to? That pole location. If I were to factor that. Yeah, z minus root. I'm asking trivial questions just because I don't want to assume everybody knows. And so that would be the location when the pole was equal to this number right here. The numerator the 0. The numerator goes to 0. Let's do a couple others. Would everybody agree I've got a pole, or a 0? I keep saying pole. A 0 at 1. Would everybody agree I have a 0 at minus 1? Would everybody agree I have a 0 at plus j? So that would be here. Then I have a 0 at minus j. So whenever z is, we are at minus j, we're up here. We're down here, and the transfer function goes to 0. The whole point of it being called a 0. Alright, so now if I were to plot, let's do this in 2 steps. I can plug the equations in. I'm not going to do that right now, but if I if I plot just the numerator, the 1 minus z to the minus 8, if I plot the frequency response, and I can do that by 2 ways. I could do it graphically, the intuitive way we talked about, or I could plug in what for z? Yeah, I could say evaluate by putting in a sinusoid that I vary the frequency, which moves me around on the unit circle. So that occurs when z is equal to, now z isn't always, this is just the evaluation. That's when I put my sinusoid in and I vary the frequency in a unit amplitude. Z is equal to j to the 2 pi f over fs, right? Whatever the sampling frequency is, e to the j to the 2 pi f ts. Remember, because now we're varying the frequency as we move around a complex plane. So if I plot this now, evaluating it that way, if I plot here the magnitude of 1 minus z to the minus 8, in the frequency domain, what do I get? Give you a hint, comb filter. Yeah, I get this, right? And what's the amplitude? 2. Okay, so now what's this first point right here, just plotting this? 1 minus z to the minus 8? 0. This one is fs over, wait, this is fs over 4, right? And this is fs over 2. So wouldn't this be halfway between? Yeah, fs over 8, or let's keep it generic, fs over k. Then this one's at fs over 2k, or whoops, 2fs over, and this would be 3fs over 3/8, be this one. This one's 2/8 fs. Looking good? No questions, right? Okay, so if I were to put a, well, this is by itself, we've already discussed. Now if I were to put the next filter we'll plot is 1 minus z to the minus 1. What kind of filter is this? Non-delaying integrator, right? So if I plot the frequency response of that one, let's do that next. You know, I want to make sure I do this right. So 1 over 1 minus z to the minus 1 is z over z minus 1. In the z plane, I've got a 0 at the origin. And then where's my pole? 1. And I know when I start my evaluation, what's the distance at DC away from the pole? 0. So the distance away from the 0 is 1, and the distance away from the pole is 0. Does everybody know that a week from today is Memorial Day, no class? And I put another homework assignment that's due Wednesday the 7th on the web. Okay. So it blows up. So when I plot, what is it over here? What's the response over here at f sub s over 2? What's the magnitude of this equal to? 1 over 2. The distance away from the 0 is 1. The distance away from the pole is 2. I get 1/2. And if I plot this, if you recall, I get a response which looks like this, where this is 1/2, and that occurs where? Yeah, fs over 2. And then at DC it blows up. Now, any questions? Okay, so now let's plot 1 minus z to the minus 8 over 1 minus z to the minus 1. This is a moving average filter. Or a sink filter. Okay, which we'll see why it's called a sink filter in a moment. Now, and we'll drive this in chapter 4, but what we get when we determine our transfer function, we cancel that 0 at DC, and we get a response which looks like this. If I did that right, so this first 0 occurs where? Fs over k. And this one occurs at Fs well, wait a sec. Now, do I have a mistake here then? So this is Fs. This is Fs over 4. This would be Fs over 8. Oh, did I? Oh, I don't have any mistake. I was one off. All right, that's Fs over 4. This is 3 Fs over 8. This one is Fs over 2. That one is 5 Fs over 8. 6. Oh, I'm off. 6 Fs over 8. And then we need one more hump. 7 Fs over 8. And then this one occurs where? Fs. Okay, so this is the frequency response, and I'm just going to point out a few things here of this filter. Okay, one is the magnitude here is equal to k, which in this case is 8. So yes, well, we canceled it with the integrator. Yeah, so the 0 at 1 is we canceled with the integrator. So if I have this filter here, let me just ask this. If I have 1 minus z to the minus 8 over 1 minus z to the minus 1, and I put in a logic, if I put a number 3 in, just an integer, at DC, based on this response, what do I expect my output to be? 24. I just add up 8 3's and output continuously 24. Okay, let's do one more thing with this filter. Let's sketch the implementation. Okay, so let's sketch the, how would I do that? Okay, so I need a comb filter. So what would that look like? That would be like this. This would be X, and then what would I have down here? Yeah, 8 registers. And would it be adding or subtracting? Subtracting. And this is now 1 minus z to the minus 8. Now what? Non-delaying integrator, so I come over here. This is y. And is it adding or subtracting? Well, it's plus, right? Because it's an integrator. So if I put in a constant 1 here, then it would come back around after 1 clock delay. And yeah, so this thing, let's just verify that real quick. Let's call this x prime. So y is equal to x prime plus x prime z to the minus 1. Right? Whoops, I got a mistake. This is y. Right? And so y over x equals 1 over 1 minus z to the minus 1. And this circuit implements this. Okay, I got a question. Oh wait, before I ask my question, are there any other questions? In this filter, if I were to put an impulse in the input, how long would it take it to appear on the output? It'd be immediate, right? Let's verify that's the case in the filter response. Okay, so how would I verify that's the case, that it would appear immediately? Well, I know I can see there's no delay, but I want to use the equation. How would I look at this and say, hey, I'm not going to have a delay? Let me what? So let's write it like this. Z to the 8th minus 1 over Z. Let's not repeat ourselves. When I look at this, can I intuitively see there's no delay in the forward path? Well, okay, let me ask a simpler question. If I had a delay, if I wanted to delay this response, what would I do? Yeah, I'd multiply the response by z to the minus 1, right? And in the numerator, or in the denominator, that would end up giving me a factor of z here. Okay, so it's not trivial to see, but because of the way the poles and zeros interact, we don't have any delay. There's no poles at the origin. Do we all remember that? We only have zeros at the origin. And a delay would be a pole at the origin. Okay, any questions on this filter? Alright, so I'm going to plant the seed and then we're going to move on, because this kind of summarizes all the stuff in the end of chapter 1, except for I want to do a little bit of review of Fourier stuff. Yeah? Because if I look at the response, oh, there we go. Oh, wait, I do, don't I? Yeah, I think it's let me stare at it for a moment. Well, let me ask this simple question. How many zeros do I have? 8. How many poles do I have? 8. There, I think that's the answer. You have to have more poles than zeros to get a delay through the filter. Okay. So, I want to just plant the seed now before we move on. We're going to talk about aliasing, and we're going to talk about decimation. And let me just talk about decimation real quick. Decimation is simply reducing the sample rate. So, for example, if I was at f sub s, this is all digital, or it could be analog, but it's all discrete time. If I was at f sub s and I decimated, I might go to f sub s over 4. Okay? So if I have a system coming in here with words at a rate of f sub s, what I do is I pass that data through a low-pass filter. And the low-pass filter is an anti-aliasing filter, and I'm going to cover that today in chapter 2. And then I resample at the slower rate. And so I've got a sampling gate. So this is my sample and hold essentially. I've got an anti-aliasing filter. Then I resample with a register. And then I've got my output at the slower rate. So I've got an anti-aliasing filter and I resample. And this is all decimation is. And so all the stuff we talk about at the beginning of chapter 2 is going to apply to decimation. But when I say this is a digital low-pass filter, in your mind you should think, oh, well, we could use that sync filter that we talked about. And the reason it's a sync filter, and again we go through it in more detail in chapter 4, is that the final response is has a sync shape, sine x over x. Okay, so this is a low-pass digital filter. If we cascade them, we get more attenuation. And this is the block diagram of decimation. So you got to have all these, both these components. This one's trivial to implement digitally, right? You just reclock at a slower rate. This one's a digital low-pass filter. Now we have at least one way of implementing a digital low-pass filter. We know how to do it in hardware right there. Notice there's no multiplications. It's all just adders and delays. Very simple and practical. Questions? Okay. So let's talk, before we move into Chapter 2, I want to just review a few things about, I have these nightmares that I ask simple questions, and very simple questions, and I don't get the answer I'm looking for. So let me just make sure we'll follow that. So let's just take a sinusoid. If I take and it could be a cosine or a sine. The only difference is a phase shift, right? So if I take this sinusoid, I write it in the time domain as cosine or 2 pi ft. Now I'm going to write this, and so this is time. It keeps going. Now I want to write this, I want to represent the same signal in the frequency domain. And let's just call that f0. How do I represent that signal in the frequency domain? Yeah, just an impulse at f0. And now in the frequency domain, what's the amplitude? Let's call this Vp. And I'm using one-sided spectrums. Yeah, it'd be Vp, right? You all agree with that? Easy, right? So when I see an impulse here, I think of it in the time domain as this. Alright, now if you recall the Fourier transform of a signal, is, and I don't throw those gratuitous 2 pi's all around in here, is g of t e to the minus j 2 pi ft dt. And the inverse Fourier and if you haven't seen this, that's a big issue because I assume you have. G of t is equal to minus infinity to infinity g of f times e to the minus j 2 pi, or positive j, sorry, 2 pi ft df. Okay, so before we show how to go from here to here, it's pretty straightforward. I want to define a few relationships. Okay. So one is the Dirac delta function. And the Dirac delta function, del of t minus t0, is equal to infinity when t equals t0. And it's equal to 0 when t is not equal to t0. Now, if you recall this should be junior level stuff. What we do is, if you look at the Dirac delta, the mathematical description we take, and we start to increase the amplitude of a pulse and then shrink its width until the width becomes 0 and the amplitude becomes infinity. But if I integrate the Dirac delta function from infinity, minus infinity to infinity, over time, its area is equal to 1. Okay, so now the next function we want to talk about is the, so this one's continuous time. Okay, so the Kronecker Dirac delta function is a discrete equivalent of this circuit, and it's only defined at sampling instances, and so it's t minus nts is equal to 1 when t equals nts, and 0 if t is not equal to nts, and I only have times at discrete instances. And the big difference here is this one's equal to 1, this is the discrete one, and this one's got an amplitude that's equal to infinity. So when I'm doing sampling in a moment in chapter 2, I'm going to be using the Kronecker delta function with an amplitude of 1 because it's only defined at discrete instances. Maybe I'm not. Let me make sure I'm not sampling. I might be getting ahead of myself there. No, I am. Okay. Okay, so does everybody see the difference? So when I do sampling, I'm going to end up using the Kronecker delta function that's equal to 1 at the sampling instances to multiply times my input sine wave. All review, right? Easy. Okay, so I'm going to do a couple other examples. One is if I take a function f of t and I multiply it times the Kronecker delta function, I'll just call it the delta function, and this is the Dirac delta function, dt. The product here is only non-zero when t is equal to t0. The product here is infinite when t is equal to t0, right? Because the amplitude of the Dirac delta function is infinite at t equals to t0. But when I integrate that function, because the width is approaching 0, I end up getting a weighted infinite response that gives me this function evaluated at t0. Does that make sense? Okay. So now, if I take and look at this function right here, and I want to ask, well, what is this equal to here? This waveform. How do I well, first off, what have I just done there? What is the integral of something times e to the minus j2 pi ft dt? What is that? No, I mean, but what is that called? That's called the Fourier transform, right? So intuitively, the Fourier transform tells me the spectrum of a signal. If I ask what's the spectrum of k or dc, what do I expect? Just going to be an impulse at dc, right? Does everybody agree with that? If I have a DC voltage of 5 volts and I say write the spectrum for that 5 volt, you go, gee, you're not challenging me. I got a 5 volt impulse at DC. So if I want to represent that using this, what would be the response? Let's just say K. And wait a sec, if I plot K, I can change frequency. That would look like this. No, it's a DC. I only have one component and it's at 0. Yeah, K times del of when is the only time I want to have the impulse? F is equal to 0, so del of F. So when F is equal to 0, this thing's got its amplitude, and I get K. Alright. Let's do one example and then move into chapter 2. No, but if, let's say it's 100 megahertz. What's the Dirac delta of 100 megahertz? What is this equal to? 0. Right? The only time this is not 0 is when I have 1 or infinity, depending on which one we're using. Right? That's why I'd put like F minus 100 megahertz if I had a pulse at 100 megahertz. Okay, so let's go back and show, just as a review, how to take the Fourier transform of this signal here. Because it was a long summer. or maybe even longer if you haven't been doing Fourier transforms. So I'll write the Fourier transform as e to the minus omega, or infinity times Vp cosine 2 pi f0 times t times what? dt. Tell me what to do. Yeah, change the cosine to terms of cosine of e. So cosine, just to be complete, we're going to be using this a lot, is e to the 2 pi j 2 pi f0 t plus e to the minus j 2 pi f0 t divided by 2. It would be 2j if it was a sinusoid. We could do that too, and it's just going to give us the exact same spectrum. What's the difference? Phase shift. Okay, so now I plug this in here and I get Vp over 2. Integral from minus infinity to infinity e to the j 2 pi t, yep, f naught minus f, plus e to the minus j 2 pi t looking good? Alright. What does this evaluate to? Go ahead. Let me see. So we got minus j 2 pi t times f, which is this term. And then the f naught would be the minus for this term. So since it's minus, 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 I think it's right. Is anybody? Okay. So what do I do now? Integrate e to the x dx. Well, you know what? I need some help. So I go back here and I look and I say, oh yeah, I got this little handy dandy equation right here which says the integral of e to the minus j 2 pi ft is just k del f. So since k here I can forget about, just assume it's 1, it's outside. What? No. It's just a weighted, it's a weighted transform. Yeah, because the Dirac delta is infinite at t equals 0. No, you don't leave it as integral. This is right. You evaluate it and it ends up giving you the Dirac delta function k times del f, and we know that del f tends to infinity and its width tends to 0 and its area stays 1. So this is what I want to use. So if I integrate from minus infinity to infinity of this, in this application right here, what's the only thing I need to do? I mean, what do I change f to f0 minus f? Yeah. So that would be times del. Am I losing anybody on that? No? Okay. So del f0 minus f plus this one, del f0 plus f There's my spectrum. This is the Fourier transform of the cosine signal. Let's plot it. Are there any questions? So if I plot it, I get let's go VP over 2. If I look at that, this term goes to 0 when f is equal to what? F0. So we go up here to F0, go up to VP, and this term goes to 0. The argument goes to 0 when f is equal to minus F0. And so that's supposed to be the same height. Now, this one's easy. What's the phase shift? If I were to ask, that's the magnitude. I can take the magnitude. That's easy. That's this. What's the phase shift? Whoops. Whatever that means. What's the phase shift? Do you see any imaginary components here? So what's the phase shift? 0. I think I should have done the sign instead. We'll do that. We'll put the result for the sign down quickly just to be complete. Okay, so I got VP over 2 this. And so the phase shift is 0. That's not that interesting. What does a negative frequency correspond to? If I have negative cosine, or if I have cosine of 2 pi times minus F0 t, what is that equal to? Cosine of 2 pi F0 t. So would it be okay if instead of drawing the double-sided spectrum, I were to just take this side and fold it over and draw one spectrum that had a single VP and an F0, right? I mean, if I'm looking at a spectrum analyzer, I'm not going to see both sides of the spectrum. I'm only going to see a one-sided spectrum, and it's just going to show the peak of the voltage if I have the spectrum analyzer set on displaying peak, that is. Could be on RMS. Are there any questions? So in going from here to here, I say that power has to be conserved. So the reason I fold this over is I sum the signals, power is conserved. Okay, so if I go back and look at this, what's the big difference here between this sign and if I were to replace this with a sign? Just we can write the result down and plot the magnitude and phase. That would be minus. That would be a J. So at the very end I'd have a minus there and a J here. Right? So if I go back and write the Fourier transform, and I know this is boring, but I want to make sure when we're going through track and hold response and all these other things that it's all really clear. Fourier of the sine of 2 pi F0 t is equal to VP over 2J times del of F0 minus F minus del of F0 plus F. Now let's plot those. Sound good? Why don't I make it easy on myself to begin with? I'm going to multiply the top and bottom by J. So that's equal to VP over 2 times J. J times J is minus 1. So I can write that as del of F0 plus F minus del of F0 minus F. Looking good? So I'm going to write now the magnitude response. Now, I look at these individually, right? There's two components. I look at the impulses individually, what is the magnitude, or where does this one occur? What's the magnitude of J? Let's ask that simple question. 1. Okay, so let's do this component first. So this is the magnitude. What do I do for this component? Minus F0, I got a component right there. So let's do down here the angle. What's the phase shift for this component? What is it? 90 degrees. Okay, so I go up here and I say, oh, it's just 90. Notice it's not defined anywhere else because I don't have any other signal there. Okay, so now I go over here and I look at this one. Okay, if I talk about magnitude and I draw it negative going as a minus VP over 2, that's really not correct, right? Because magnitude is the length, and you can have a negative length. So I'm going to go ahead and sketch the magnitude as its length, because the minus sign is just a 180 degree phase shift, and that's also at VP over 2. But now I multiply the J through, and the J gives me 90 degrees. But then I have this minus sign, which rotates me down another 90. So that gives me a phase shift of minus 90. Okay, so now if I go combine these and draw the signal as a single-sided waveform, okay, power has to be conserved. If I sketch and draw these over, I fold this one over onto here, the magnitude of the one-sided spectrum becomes VP. The power in each spectrum is conserved. Can I do the same thing for my phases? No. Okay, I can't draw the one-sided spectrum for the phases. Now, if I understand that, that means that sine of 2 pi minus ft is not equal to sine of 2 pi ft, because it's not an even function. But if I ask, well, what does this negative frequency mean? I don't understand that. That scares me. Negative frequencies. I don't like drawing negative frequencies. Well, that's nothing more than rewriting as sine of 2 pi ft plus pi. Just a phase shift of 180 degrees. Does everybody see that? So if I look at the phase shift between those two signals, I have 180 degrees. Well, I can draw this signal over here in the negative and with negative frequencies is just having a phase shifted positive frequency signal. So now if I do that and I add the signals, well, okay, the phase shift between here and here is 180, but it's still, I don't still see how I can draw a 180 degree phase shift. I might be able to get away with drawing the minus 90 or something like that, but it's really not correct. So that's why we won't draw the one-sided phase response. Alright, are there any questions on that? Easy, right? Review? Alright, well, I think I've gone over that more than well. So if somebody says, if you're standing in the line at Winco and somebody says, I just don't get negative frequencies, can you explain those to me? You say, oh, it's just a phase shift. And that minus f, it just means it shifts it in time. Okay. Of course, you could argue, and to be precise, well, wait a sec. How do I, if I only have one-sided spectrum, I draw it one-sided, how do I go back and represent that with a cosine or a sine? Yeah, that's where it gets a little confusing, right? Because if I try to fold it and combine it, you know, how do I represent it? I have to go back to the spectrum of the sine wave and go from there, or represent it with exponentials. Okay. Back on the farm here. Let's go talk about this in chapter 2, sampling. And page 12. Okay, so in sampling, what I'm going to do, I'm going to take, and I've got a multiplier, and I'm going to multiply an input signal, let's call it, just to be consistent, x of t, which is Vp sine of 2 pi Fn times t, and I'm going to multiply that times a delta function. What did I call it here? You know what? Let me make sure. I'm always looking for type. It's Dirac delta function. The discrete version of the Dirac delta function is the Kronecker delta function, or simply delta. Okay. This is the discrete version of the delta function, and that's del of t minus nts. So, just as a sanity check for myself, let's sketch, and so the output is, if this is the sine wave input, my output's going to be defined at certain instances. And so the length of those instances are my sample values, and it's not defined or it's undefined in other places. So if I want to sketch this in the time domain, what does it look like? Just so this would be time. This would be 0 nts, n plus 1 ts, n plus 2 ts. What is this one? Oops. And what's this one? They're spaced apart by what? Ts. Boring, I know. Okay, so if I want to write the output of the sampler, so this is a sampling gate. If I want to write this output, what is it? What did I call it here? Y of t. Y of t is equal to, yep, sine 2 pi Fn times t times a delta function, which is del of t minus nts. Now what I'm concerned with is, what does the spectrum look like in the output? So what do I do to find the spectrum? Take the Fourier transform. So I take the Fourier transform, minus infinity to infinity of Vp okay, now what? Look at page 28. Well, I've got over here a bunch of impulses which I can sum. Let me follow the book. N equals minus infinity to infinity, because I really have a summation here, right? I have to have the summation of all of those, n equal minus infinity to infinity, because if I just pick one, set nts, I need to have all of the spectrum. But if I take and look at that sum of the impulse functions, and I write, or I look at its representation, and this is a Fourier series, and so this is a periodic function corresponding to my sampling impulses. I want to represent it in the time domain. Fourier series allows me to calculate the coefficients and represent a periodic function in the time domain. and that was the first part of the last section in chapter 1, which I skipped. We can only do so much review or else we won't cover anything in the class. So t sub s, and that's n equal minus infinity to infinity of e to the j 2 pi nts, or nt over ts. So ts is also 1 over ts is also what? Yeah. Looking good? Alright, so if I ask what's NFS represent? Periodic tones at a period of f sub s, right? Now I look at this and I go, okay, well, how do I use that? Well, what I'm going to do, I'm going to plug this into the Fourier transform here, represent the sign using the e to the j minus e to the minus j stuff over 2j, multiply everything through, and if I do that, what I end up getting is that the output of the sampler is Vp over 2jts from k equal minus infinity to infinity of, I'm sampling a sine wave, so I expect the output to be just impulses of that sine wave at various frequencies, f minus fn minus kfs minus del of f minus fn, or plus fn, minus kfs. Alright, so this is good because we already talked about the phase shift where we have the j and all that. Okay, so let's write, or let's sketch the frequency. So, and I'm going to assume that Fn is much, much less than Fs. So what point should I pick first? How about k equals 0? So if k equals 0, what's my output look like? Yeah, should I draw the minus here to sketch it? The magnitude, if I draw the magnitude, it's going up. Would everybody be okay if I just drew the magnitude? Okay, so I get a tone at minus Fs and a tone at F sub s. Yay? Or, whoops, Fn, because k is 0. So this goes to 0 when f is equal to Fn and f is equal to minus Fn. Then if here's F sub s, where's my next tone when f is equal to, if k is 1, this goes to 0 when f is equal to Fn plus Fs, Fn minus Fs for k equal 1. So that would be, like one tone here and one tone there. This would be at F sub s plus Fn. This is F sub s minus Fn. What if k is minus 1? Whoops, I'm off. This should have been minus 1 here. And then if k is 1, then we get it going over here at f sub s minus Fn and minus f sub s plus Fn, etc. And you've all seen this before, I assume, right? Okay, so bottom line is we get all these aliases. if I want to recover the original signal, what I have to do is I have to pass, okay, so before we go any further, what's the amplitude here, the weighted amplitude? Because we know, well, it's VP over 2TS, right? So if I want to get the exact signal replica out, I need to pass the spectrum through a low-pass filter and remove all of this other stuff, so I'm left with my original spectrum. Does everybody agree with that? Okay, so what's the magnitude of the filter have to be? This is my reconstruction filter. No, it can't be 1 because then I don't have, remember my original sine wave has an amplitude of VP over 2. Well, it has to, well, not 2 times, because remember it's original spectrum. If I look at it, VP over 2 is what the impulse's amplitudes are. So I have to multiply, I have to pass this through a filter with an amplitude of, not 2. Here, these have amplitudes of VP over 2TS. The original spectrum, what I had before, was VP over 2. To get that back, I need to multiply TS. Or I could write it as 1 over FS or TS. That's the amplitude of the reconstruction filter. Okay? So now, if you go through when we talk about the sample and hold, our reconstruction filter may have an amplitude of 1, and that's because we don't have these little impulses with a minuscule amount of power. We hold the signal the entire time between the sampling instances, so that when we pass the signal to the output, we pass through a reconstruction filter. We don't need this weighting here in our reconstruction filter. And that's why this is using this kind of sampling in analog circuits is somewhat academic, because we can't process a signal if it only lasts for 0 time or a very small amount of time. Okay. Having said that, the key point here is that using impulse sampling, you can get the exact signal that you are sampling back. When you use a sample and hold, you introduce distortion into the waveform, and you have to do other things to get the exact sample back. So let's briefly talk about that reconstruction. So I'm going to do this 2 ways. Let's do it this way. If I look at my ideal reconstruction filter, and I'm going to ask a trivial question here. So I've got my filter here. This is the magnitude of my reconstruction filter. And the magnitude response is TS. Alright, I was going to cry if you didn't get that one. Alright, what's the cutoff frequency here? FS over 2. Because you can easily convince yourself that if you don't keep F in less than Fs over 2, you get aliasing down in your desired spectrum. Okay, so I want to determine the impulse response of this filter. So I have a filter here. Let's just call it the reconstruction filter. It has this response, a magnitude response of TS, a bandwidth of F sub S over 2, and a brick wall response. How do I determine in the time domain, if I want to look at the output here, I want to determine this filter response, I can do a couple of things. I can just apply a source, and I sweep the frequency, and then I plot the output, right? Another way is I can apply an impulse to the input, and then I can look at the response on the output here, and then take the Fourier transform of that response, and that'll give me my transfer function. Does everybody see that? Okay, so what I'm going to do is go the opposite way. Does everybody follow that? So transfer function is nothing but the Fourier transform of the impulse response of a system. Right, you can take and look at the oscilloscope trace and then take the Fourier transform of it, and it'll give you the transfer function of the system. So I have the transfer function already. I'm going to go backwards. I'm going to take the inverse Fourier transform of this filter, and I'm going to look and see what the impulse response is in the time domain. And if I do that, this is the top of page 32. What I end up getting is a impulse response. If this has a frequency domain response h of f, I get an impulse response h of t, which is the sinc sine x over x of pi fs times t, and the impulse response then looks like this. So here's t equals 0, and then here is the first point is at t sub s. This point's at 2t sub s. This amplitude is 1. Now here's some key things that are good to remember. At ts over 2, this amplitude is 0.64 or minus 3.9 dB down. You see that? And this peak here is 0.21 d, which is minus 13.5 dB. So before I talk about this in more detail, this is the exact shape of our low-pass sinc filter that we talked about earlier. When we plot the magnitude response, of course we don't have negative numbers when we talk about magnitudes, I get a response that looks like this. This low frequency response is 1 or 8, and then this response here is 0.21. The first lobe is at 0.21 of the peak. Okay, so I don't get that much attenuation, and so to get more attenuation I have to cascade these. So if this peak was at 8, then this first lobe would have a response which is 1.6. Does everybody see that? Any questions? Okay, so now here's the rub. When I apply my pulse at t equals 0, this is the shape, time domain shape I get out. This is the ideal reconstruction filter. The rub is that, hey, my output starts occurring before my input. So I apply my impulse right here, and my output has already been running. It already occurs, right? And so I can't make this filter. I can't make an ideal brick wall analog filter. So I can do one of two things. One is, okay, does everybody understand that? So I can do one of two things. I can either increase the sampling frequency while keeping the bandwidth of interest constant so that I oversample the input. So I go to 100 times higher sampling frequency. That means I can then use a filter which rolls off slower. Or I could reduce my input signal bandwidth. Okay, if I reduce my input signal bandwidth, then I can have a slower roll-off filter. Okay, so I can't make this, so this is somewhat of an academic discussion. But I want to show you before we move on to talk about the sample and hold, and maybe we won't do that today. Everybody looks tired too. Actually, we need to talk about decimation before we talk about the sample and hold. I want to show you, and you know what? Let me just show you in this picture. If I take, and I got my impulses here, and I just add, you know, the output, because their output's going to be the sum of the impulses. If I take all those sinc responses and add them together, sure enough I get exactly my input signal, because sometimes the sinc response is negative, sometimes it's positive, but when I add them all together they all sum to my exact response. And so that's how I can reconstruct my exact input, is by passing it through this ideal reconstruction filter. Any questions? Alright, let's see. Let's do decimation real quick, because I already hit on it briefly. Okay, before I do that, if I want to go from a clock frequency of f sub s to a clock frequency of s sub s over 2, what circuit in hardware should I use? So just this, right? If I D, Q bar, feed that back around, clock this with F sub S, divides by 2, and this output becomes F sub S over 2. If I wanted F sub S over 4, I'd use 2 of them, right? Okay. So now decimation. And so why would I want to use decimation? If I'm storing the data, it's less data to store. If I'm transmitting the data, it's less data to transmit. If I want low power, I don't have my multipliers running at as high as speeds. There's lots of reasons I want to slow things down. But now, if I slow things down, I also have to reduce the frequency content of my signal. I can't have very high frequency signals or else I end up with aliasing. Okay? So in decimation, which has a block diagram that looks like this, I downsample by k. If my input's coming in at a rate of x of nts, I might have my output going out at a rate y of, I'm going to be a little different from, we'll do it the same way the book does, ki times ts, where I'm decimating by k. So if I look at that, I is a different index, so if I add a decimation by 8, I might add up the 8 inputs, output results. Then not do like I did the moving average, where I just took the next 8 outputs, but wait and sum the next 8 outputs, output 9 through 16, and output the result. So to make sure that's clear, let me do it with 4. If I have x1, x2, x3, x4, x5, x6, x7, x8. Remember, originally we talked about there's 4, then the next 4 is here, the next 4 is here. If I'm decimating, I might add up these 4, output the result, add up these 4, output the result, and so I'm going at 4 times slower rate on the output. The frequency response to that filter is exactly the same though. Okay, we'll cover this again later. Are there any questions about this? So the way I would do it, take my x of nts, go into a low pass filter, sync filter for example, that we've already discussed. This is coming in at f sub s. This data is coming in at f sub s. Go and resample the data at f sub s, in this case over 4 or over k, and then my output q here, so I don't have to do multiplication, I just resample, is a decimated output. So let's do a simple spectrum or simple example and then quit. Are there any questions? This is, I find talking to people, they don't understand decimation as this simple process. Anti-aliasing filter, resample. There's different ways of resampling. Again, we'll talk about this later. Well, this thing right here, when I sum the 4, that's a low pass filter. Okay, that's providing this action right here, because when I sum the 4, I get that sync response. Okay, so then I output the result. That means after I wait 4, I clock it into a register, and then that's what I get my output. You know, the register may be in the low pass filter. It may be just something you clock every 4th time. Okay, so let's sketch a spectrum, the spectrums, and then call it a day. So we got something that looks like this. So I've got, now my data's digital, so I'm going to make a mistake. If my data's digital, I say, oh, the data's band limited here, and let's just say this is f sub s over 2. Why is that not digital data? So this is my data. It's got some spectrum, it's moving around. Why do I know that's not digital data? No, it could be continuous spectrum. I think that's what you're saying. It has to be a discrete spectrum. No, it can be continuous. What do all digitals, the spectrums of all digital data do? Repeat. So I go up and I go back over, and this one's at f sub s. So that's my digital data. Now if I'm going to decimate, it's just like analog way. I can't decimate if I want data out here because then it'll alias. So I have to have some limitation on my data, right? So I might want to only to say this amount of data here. A great example of decimation is compact disc players or MP3 files. They encode or decimate with a really good sharp cutoff filter, and that's how they are able to store less data, right? But that's decimation right there. Okay, you pass it through the filter, remove the frequency components, and then does anybody know what the sample rate is on a CD, for example? F sub s? No, it's 44.1 kilohertz. You know it's got to be greater than 20 kilohertz because they want to have good fidelity in the audio spectrum, right? So you can't go any lower than that, but you can imagine when you're recording music or saving music, you don't want to record it at 44 kilohertz. You want to record it much higher because you get a better signal to noise ratio, but then when you store it, you want it to go down. Okay, so let's limit our spectrum to here. So this is my desired spectrum. So this is after the anti-aliasing filter. Yay. And so what is this point right here? That would be f sub s new. I'll just call it divided by 2. And then as I resample at the slower rate, and let's just draw it here because they're really anxious to get in this room. So I redraw it at the slower rank, I get my the slower rate, I get my aliases because I'm resampling at the lower rate. So I get this. So this would be my f sub s new. This would be 3f sub s new over 2. Any questions? All right, have a good day. We'll see you on Wednesday.